So let us now define restoration as an inverse problem that we can then solve also in a case when we do not know enough about the degradation process and the degradation model, but we rather apply some optimization process, some iterative process that leads gradually to the desired original image estimate. Some of the formulations that we already are very familiar with are now repeated here. So again, degradation model with the input function, original function, with the degradation model, which then acts by through convolution with the original unknown image. Then there is some undesired noise, which is assumed to be additive in this whole lecture. All that to get some, to reach some observed image, which is then corrupted, and we're not, we would like to use it in order to get back to the original, which we can then use further for more reliable analysis. So we then somehow identified that we have a forward problem here, or formulation of a forward process rather, which from the original image in this convolution and addition leads to the observed image. But then we can also look at the inverse problem. If we have the degraded image, can we then reverse the process with this added noise and this convolution and get back to the unknown image? So inverse problem here means that knowing the result, we would like to recover the input. Of course, we are again talking only about estimates. So we are estimating the input, and in most of the realistic cases, we will not know if we reached the original image, because if we knew the original image and could compare with it, we would probably not go through the restoration at all. But now just emphasize here one way of seeing what we can try to do. If we cannot directly reverse the whole process as we could when we applied inverse filtering, then we have one operation, let's say division with the Fourier transform of the point spread function in the Fourier domain. Now we are iterating, trying to find f that if so we have some tests, some proposals of f that we let go through the forward process and see how that they behave and what they generate at the end of this forward process. And then we are essentially looking for such a function, such an input, such an estimate of f, which, if subject to the same degradation, will essentially lead to the output which is as the same or as same as possible to G. So in order to find something that is as similar as possible to f, now we are trying very many different possible options for f. We are using the forward problem, and we are looking for the results which are similar to G, which we have, the observed function, saying that once when we find input which leads to the same observed image, or very similar, that we actually have, then we can say that this, what we have now, is a reasonably good estimate of our original image. This is essentially a classic type, a classic inverse problem, what we are trying to solve now. So we know the outcome and we want to know the input. Inverse problems appear, let's say, everywhere and are very much studied. There is, let's say, an analysis of inverse problems, and then it is said that an inverse problem is well posed in the sense of Hadamard. If a solution to this inverse problem exists, if it is unique, and if this solution is stable enough so its behavior changes continuously with the initial conditions. So the way I change my initial conditions, I slightly change my whatever I have, H or J, my solution to the inverse problem will somehow smoothly, continuously follow my changes of the initial conditions. So I can a good control of that unique and first of all existing solution. But it is often that inverse problems are not so nicely behaving and not so easy to solve. It is said then that they are ill-posed. And then they're quite difficult to solve. It most often means that we are lacking conditions, we are lacking information. That means we are lacking some constraints that will help us find a suitable solution, even if that one exists. So that would mean, for example, that we are lacking equations in our system that will determine our solution, and then we know that that we so often need to, let's say, add some additional constraints that will help us to solve the problem. And also that we might need only to meet all the conditions only approximately and not exactly, and therefore we are formulating optimization problems which will not really require that we find F which leads to equality here, but we find F, or we find some unknown input which will lead to proximity here, and we'll actually say that the difference between what we have here on the right with that particular input is very close to what we have on the left. So not necessarily equal, but very close, or a result of some minimization. As already commented, in this process of finding an argument that minimizes the difference between this forward process and the actual result, forward process for a selected input, and the observed image or our result of the degradation, we might want to add some additional constraints to this argument that we are trying to find, and which maybe minimizes this term here and really reaches minimal difference or very suitable difference, but might not be fulfilling some other constraints that we might want to impose, or simply does not lead to a good solution because we don't have enough of constraints to reach the solution. That means that we often have to add some constraints in this objective function of our optimization problem. And these additional constraints are often referred to regularization terms, or one term. since now we have two terms, one of them which is then based on how the, in our case, images look or how our input and output differ, is called data term. And then we have regularization term. And both of them now are included in the optimization, where this first one is actually given by our problem and the data that we deal with, while this other one is something that we impose based on some a priori knowledge or some desired properties of the solution that we would like to impose. Then we also include a regularization parameter in this equation, which allows that we set suitable, let's say, weights or importance to these two different terms. Sometimes we want to give more importance to these additional constraints that we want to fulfill, our solution to fulfill, and then we will have suitably, let's say, high regularization parameter that will simply give more importance to that term. Alternatively, we might rely on our data and give less importance to these additional constraints. Then our regularization parameter should be set quite low and will then give higher importance to the data itself. So this here that should be minimized is then called energy function. And then we are looking for an argument here. We are looking for an argument that will provide the solution with minimal energy, so which will lead to the minimal value of this energy function. These are already commented, and then again this final comment is that this difference between the let's say forward process and for a given argument and the observed image that we have is often measured in, let's say, in Euclidean sense. So it's most often squared Euclidean distance or norm, which we apply here to measure the difference between the images. So if we, as so far we did, we assume linear degradation model, which can be expressed by convolution, as we know, to include that information in our energy function means that we simply don't use a general expression as function h acts on input u, but we know that such a linear degradation can be expressed as matrix multiplication, which then very much simplifies our work with this function and its minimization. So here we have then notified that we can use matrix multiplication, and then I also mention or remind you that if we want to, that it's quite easy to represent filtering or convolution of an image with some kernel with the filter. As a matrix multiplication, images are then often expressed as vectors in some suitable way that we will just agree on and stick to. Whereas convolution kernel will then be put in this convolution matrix or Toeplitz matrix, which has this characteristic repetitive pattern of the values that appear in the kernel, so that when we apply ordinary matrix multiplication with this Toeplitz matrix and the vector representation of our image, we can get to, again, suitably organized resulting image now in a vector form, and by that implement very easily any convolution being linear as matrix multiplication. How does this work if we want to to perform denoising of an image. So how does the energy function work in this case? And also, what is a suitable regularization? Now, we are looking at a concrete degradation model, which then is a unit, which uses then unit matrix or function here. So there is no other degradation than noise present in our image. Our formulated optimization problem is then of this form. So here there is only an image that we kind of say this is a trial, and we compare that image with the observed image, and we are trying to stay close to the observed image while still adding some regularization that will impose some particular characteristics that we want to preserve in our image. It is quite clear looking at this example why this regularization is so important. If we don't have this regularization that imposes some additional constraints that we want to preserve, our energy function would reduce to like looking for an argument, looking for a function u, which will minimize the difference between u and the observed image g. And quite obviously, that will be image g itself. So we will not really manage to change it in any way by performing this optimization process. So this additional constraint actually makes this, this optimization non-trivial and leading to some desired result. So in this case, our transformation matrix is simply identity, and this is what we have to deal with. This is again, as commented, the difference between the images is then measured in the using Euclidean distance, which is suitable if we are dealing with if we know that our image is corrupted by dominantly Gaussian additive noise. And as we know, this is a typical assumption which simplifies a lot of derivations, but we also should know that it is not always, it does not match reality. However, if we want to come closer to a probable realistic degradation model, and for example include Poisson noise or mixed noise, then this whole model can be followed, but it will require some further adjustments, which we will not go into. But again, it is good to have in mind that some of the realistic scenarios might have to deviate a bit or get more complex than this this story that is, however, often used, but is not always perfect for every scenario. So now we know that we know everything about this data term. We know that we need regularization, but we don't really know yet what is a suitable one. So what should we use as regularization? So this is something that we want to impose to our solution, knowing what is desired in a certain situation, or even or some additional imposed criteria, something about concrete application, or whatever else we can formulate and say this should also be considered when we do our restoration and we try to recover our image. If we have if you want to denoise our image, so we want to remove noise, we know that that means that we want to smooth our image, that we want to remove fluctuations in image intensities, and that, as we know also from our lectures related to filtering, we know that we want to minimize the gradient in our image. We know that gradient will sense changes in our image. We know that gradient has high response in a noisy image. We remember some of these illustrations. We know essentially that in order to find edges, we first have to smooth our image and to remove noise, which will affect gradient to respond strongly. So we want to minimize gradient. Nice. What do we do? Well, we can then say, let's take the gradient of our image, let's square it and take a sum over the whole image. So we have sum of squared gradient magnitudes, and let's use that as a regularization term. So let's say that we want to have an image, to come to an image that is close to the one that we have, but has also this minimized gradient. It has attenuated high fluctuations. So this is what we're looking for. This choice of regularization has its very nice properties and motivation. First of all, it's intuitive. We want to deal with the gradient. We want to minimize it. Why do we use square here? Well, that's a very good first attempt, good choice, we think, because simply we need to optimize this, and we know that quadratic functions are quite easy to, like they're convex, and then they behave well when we want to, when we perform optimization, we can easily deal with them and find global optima quite easily. But now when we observe what happens if we have an original image and we have its noisy version, and then we want to perform this restoration or denoising by energy minimization, and we use this model with this particular Tikhonov regularization term here, then we see that it is quite impossible to find a good amount of regularization that we should impose and get close to the image that we would like to recover. If we regularize so that we don't impose this gradient minimization to a high extent, so we use small lambda, and we let our resulting recovered image be kind of dominantly close to our noisy one that we compare with, then we don't really simply remove enough of noise. Now we act as, okay, but let's then push a bit more on this regularization, and by that let the difference between the image that we are generating and the original one that we start from, and the degraded one that we start from, the observed one, grows a bit higher. Well, what happens is that then we get to this type of an image, and that means that we simply left the original image a bit too much, or the actual image a bit too much, but we also see that we got very smooth edges as well. So we observe the same behavior as we did when we did smoothing by filtering, that majority of these filters suffered from the problem of, when smoothing enough to remove sufficient amount of noise, they were also smoothing our desired edges too much, because it is hard to set a balance what is a desired sharp transition in the image and what is undesired coming from simply noise. So what can we do to address this challenge of setting the right balance between suppressing small variations, which should be noise, while preserving those larger intensity variations that presumably correspond to edges and details that we want to preserve, and therefore should not be smoothed out. So we should somehow try to design regularization that will act differently in the regions where intensity variations are small, they should be suppressed, and where intensity variations are large, which should then be kept as much as possible as such. And then it happens that change of a regularization is, at least from like a higher level view, quite simple. Let's just not square the gradient magnitudes. So instead of looking at the sum of squared gradient magnitudes, let's just take a sum of the gradient magnitudes in the image. This regularization is known as total variation regularization, or TV regularization, quite known as such. And it appears that that one actually gives better results, which we will soon see. We can just comment on why, at least on a higher level, why that is the case, or why that is kind of intuitive or expected. So if we look at a whole family of functions which then contain also those two that we were looking at, TV is then a function where this p here is equal to 1, and then that is like taking, this is the set of norm functions. So this then means that TV corresponds to taking L1 norm of gradient magnitudes. If p is equal to 2, and then of course there will be square root, then we will have what is then observed at the previous slide, and is Tikhonov regularization. So that would be L2 norm of gradient magnitudes, where the square root can be in the optimization. We can ignore it because it does not really affect the result when the square root will be minimal for the minimal value that we take square root of. So that is only for the optimization when it doesn't matter. Otherwise, the full expression is with that square root. So we can just remember that. So if we look at how these different functions, norm functions with different values of p look when plotted in 1D for simplicity, then we see that, so this is what corresponds to L2 and would then correspond to Tikhonov regularization. P1 is this then what we see here, and is somehow absolute value. This is ordinary quadratic function. And then we can go further with P, which decreases further and has this kind of, and then it is concave and gets more and more concave with this peak here. But what we can then see as the main relevant behavior and difference that is relevant for us here is that when squared, values that are close to 0 get even smaller, get smaller and smaller, while values that are then high, once when squared, they really grow quite rapidly. That does not really hold for, let's say, P1, L1 norm, which corresponds to this P equals 1 here, where the values are kept the same, both when they are small and when they're big. If I put that in the context of my optimization, that means that my regularization, which corresponds, Tikhonov regularization, which corresponds to LT norm, will essentially, by squaring big values, will act much more on them and will suppress, in order to reach the objective, much more the high gradient variations, high gradient values, while will not so much act on the in the small regions. Because of squaring small gradient values, they will become anyway even smaller, and my optimization will not have to, let's say, work much on them. While with L1 or TV regularization, I will act on comparably, I will act more on those small values which correspond to noise. So they will be more visible to my optimization problem, and that will be therefore more suppressed. And comparably, high values, which will correspond to my edges, will not additionally grow and will not be so much suppressed as they are if I use Tikhonov regularization, which means that I have better chances to preserve them, actually. So that is some intuition behind using TV instead of, let's say, Tikhonov regularization for better noise suppression while preserving edges. So this is an example where we have something very similar to what we already were looking at when we discussed presence of noise and how to analyze success of our restoration when looking at, for example, when analyzing noise that we have removed or compared to what we know that we have in our images. So here I have my original image that I add noise to that image. So this is Gaussian noise, normally distributed noise with sigma equals to 0.1 and mean equals to 0. So this is just to keep on mind for a short while. And then I have this observed image. So this is what I call G in this notation that I use. And I also can measure, let's say, the quality of this image by expressing its signal to noise ratio, and that one is 9.75 decibels. We know that that is not a very good image because we talked about desired values which are certainly exceeding 20 to be called acceptable quality. Okay, so I have this image, I work with that one, and I would like to get as close as possible to this one in my restoration. And now I'm using TV regularization. And I have different values of lambda, so that is that regularization parameter, used in these three examples that I'm showing. And we can observe a bit different effects of these different values of lambda. So this is my recovered image, my estimated image. This is what I get as a result of my TV restoration by energy minimization that I'm applying now, and I'm using TV regularization. So if I compute this, so this image here is computed by taking the difference between estimated and observed, the noisy one that we had on the previous slide. So this essentially shows what is the noise that we removed. Estimated minus original then shows the difference between what we obtained in our restoration and what we would like to have obtained. So this is what we are aiming for. This is the noise-free image. This one should look as much as possible as normally distributed noise. So with no structure, with no visible details, which would correspond to the image itself. This one should be flat because ideally these two are the same, and they are then the difference is simply 0. So in this case, I'm also giving, or in all these cases, here is information about signal to noise ratio for the generated images. So the previous one was not, the starting one was 9.75 decibel. Now we have, in this case, 15.25. Okay. This here is then also characterized by the standard deviation of 0.9. So it actually corresponds to the parameters of the noise that I added. And in that sense, this should be a very good result. And that one is obtained with lambda equals to 0.2. So that is a choice for a parameter lambda, which will say how much I trust my data, how much I want to rely on this simple difference between the image I have and the image I am kind of proposing as the corresponding original, in contrast to this imposed criterion that my gradient fluctuations should be, my gradient values and intensity fluctuations should be small in the TV regularization sense. To somehow observe the effect of lambda, we are then taking two other values, one smaller, which is then, let's say 0.14. This is the estimate I'm getting. Again, the noise I removed, and also this is the error of my estimation. So how much my estimated original, my estimated version differs from my original that I would like to get. What I can observe is that signal to noise ratio in this case is higher than what I got previously, and that is the best I can get, or I got in these cases, and that is then also with noise which is estimated to be different from the actual one that was applied. So that is also something to observe, that there are a number of parameters here and that they are not necessarily always somehow straightforwardly combined into, let's say, that they don't, that in this particular case, that estimating noise correctly does not lead to the best signal to noise ratio, which would then be one criterion to say that this is then the best estimated image, this is the most suitable estimate of noise, and so on. So there are different criteria and different parameters that sometimes are not speaking in the same direction. One more attempt to use different lambda. So now it is comparably higher than both previous ones, which means that we are imposing more of that a priori knowledge. We are imposing more of this suppression of this of the gradient, high gradient values. And also by that, leaving this, like letting our generated image be more different from the one that we are starting with. That leads to a relatively poor result. So signal to noise ratio is now down to 12. So it's the worst out of these. Sigma, however, is, let's say, not in a way, it's still close or equally close to what we had estimated when we were very happy with signal to noise ratio. However, we see here that our removed noise contains much more structure than, for example, what we have here. And that is a clear sign that our restoration is not really successful, since we would like to have removed noise that is indeed with no structure, that just corresponds to randomly, normally distributed values. This is then, again, to test how flat this difference is, and we again have a indicator that this was not a very good restoration. So this was a bit of examples how the different values of lambda affect the result of restoration, how much we should regularize our energy function, or how much we should trust our data, or how much of this a priori knowledge we should impose. And in principle, it is not at all easy to know what are the right values. It can be very much that this is application dependent. It depends on imaging. It depends on particular application. It depends on a lot of different factors that we cannot easily have an overview of. There are a number of methods that can help to automatically estimate what is a suitable level of lambda for our applications, for our images that we work with. And I listed some names of, or as I say, keywords for these different methods, but I will not go into details and I will not go further into that direction. You are very free to explore this if you're interested. So all these will help me select right amount of regularization and set right amount of how much I trust in my data and give importance to the data term compared to how much of a priori knowledge I want to impose and therefore give higher relevance to my regularization term. TV regularization now is somehow put forward as a very successful regularization when we want to perform denoising, and it is indeed, let's say, it improves significantly compared to Tikhonov regularization, for example, that we mentioned in the beginning. Of course, there are still some challenges, some problems that remain and have to be especially separately addressed. So total variation is convex, but it is not smooth at zero. We noticed that peak that is characteristic for an absolute value function, this is a disadvantage compared to L2 norm or Tikhonov regularization, which is quadratic. So this behavior, this property can have negative or does actually complicate optimization, gradient-based optimization. So there are some issues that should be resolved there. There is some loss in geometry because some edges, some corners are still lost, even though to a much higher extent than with, for example, L2, that is Tikhonov regularization. There are some observed effects, such as staircasing effects, which then mean that we have some edges sometimes appearing in even in flat regions where we do not expect or want them. And again, loss of texture would mean that it still is not totally easy to have a global decision which then differentiates, okay, we now managed to differentiate noise with, from edges, and that is quite big difference in fluctuations, hopefully. But if we talk about texture, that is then actually quite small intensity variation often, and that is really difficult to differentiate from noise. And in that sense, now we have a remaining problem. Okay, now we know how to suppress noise and reasonably well preserve edges, but how to suppress noise and preserve also, how to suppress noise while preserving texture is still not easy and not solved by total variation as proposed so far. So there are some solutions to these problems. So total variation is often approximated with a quadratic function at zero, so that it becomes the resulting approximation becomes smooth. We can do some refinements. There are ways to address this problem of loss in contrast and loss of geometry, so which results sometimes in simply shrinking of objects, and that can be also addressed in suitable ways. There are solutions for that. We can have some generalized versions where instead of looking only at gradients as first derivatives, we can include higher level, higher order derivatives, and by that maybe include some additional, let's say, sensitivity when we perform regularization, when we impose criteria, what to preserve, what to not preserve. And we can also have some other functions that act on the gradient that we are definitely interested in, and by that try to, let's say, preserve, to have a better, finer selection of which details we want to preserve and which we consider noise and want to remove, or address some other issues that may happen with total variation as originally defined. Can we extend all this, what we described here, and address some other degradation types, since that's what we talked about and that's what we would like to include here? And of course we can. And that actually now when we know the methodology, now it appears actually quite simple to extend this, what we talked about so far, how to remove noise by energy minimization. It is quite easy to include other types of degradation, especially if these are linear, and that is what we were mostly talking about so far. That's the restriction that we anyway imposed. Why is that so? Well, if they're linear, and that means can be modeled by convolution, then they can also be expressed as matrix multiplication. And that means that we will simply have this change here. Instead of having just our image, our function u, we will then also apply this linear degradation to it in this forward model. And we will then just kind of repeat or take this whole process, optimization process, in the same way as what was described for for the case of denoising. And that is the whole thing. So as long as our degradation can be modeled by convolution, and that we can derive a corresponding matrix to multiply with, we will use that in this forward model. So instead, when taking an image, our initial guess, or our guess for a right image, then we are pushing through the forward model. That means that we're applying this particular degradation. We are comparing with the degraded image that we have, trying to actually get the right input, so that once degraded, it is actually the one that we got. And for the rest, and that is mainly to address noise in our image, we are then staying with the same regularization, and that is this total variation regularization that we talked about before. So in this case, we have an image which is both degraded by blur and by noise. Its peak signal to noise ratio is reported here. If we know, well, that is of course always an important part of the story. If we know point spread function, and that is essentially the model of the degradation that acts here, that is used to convolve the image, and by that model the degradation. If we know that, then we can run our optimization procedure. And we can, in this concrete case, using the information that our degradation is a point spread function with Gaussian with sigma equals to 3, we can recover this image, which now has peak signal to noise ratio of 22, so increased compared to the previous one. And we can observe more details in this image, which means that we really got rid of or reduced blur. That means really managed to address this particular degradation. And presumably we also managed to reduce the amount of noise. So that would then be the same procedure, the same optimization problem, even the same regularization, which now can be applied to remove both blur and noise from our degraded image. Important thing again is that the question on how do I know what is my my point spread function, or what is the matrix that I should use here to model my degradation, brings us back to the previous part of this lecture, which says something on what can be done to know something about the degradation model. But also in that part, we also discussed that it is not at all easy, and that there are different ways to deal with the problem. What I can comment here is that there are also there is a possibility to do what is called blind deblurring, and that one would essentially follow the same idea, but will then allow to perform this optimization in a way that kind of simultaneously optimizes and recovers both the unknown original function and the unknown point spread function. So if we don't know anything about point spread function, if we don't know enough about our degradation, we can still find algorithms or formulate this very similar optimization process so that we simultaneously optimize for both. Of course, the outcome, the result, will in general not be equally good as if we knew the right formulation of our point spread function, but will still produce some result. And if we don't have any better option, that is then a way to go. Can we do further generalizations? Yes, actually, then we should just be again reminded that that the key thing which reflects what is the type of degradation that we want to deal with is then included in this part of our equation here, and in particular in this what is used to multiply our, let's say, image, our running image, our guess for the restored image. And as long as we are able to formulate degradation that we are interested in, and we would like to recover or undo, as long as we are able to express it as long as it is linear, which means that we can express it as matrix multiplication, we can use the same model and actually repeat the whole story and recover a number of other linear degradations that we may experience or have in our images. One such example is, for example, if we have some subsampling. So we have we would like to actually recover our image, which is potentially degraded by noise, by blur, but is also downsampled. So we would like to recover its original appearance, which means that we would like to remove noise, we would like to remove blur, and we would also like to have it upsampled to the original, let's say, size. And that is also possible to include very easily, because this subsampling can very easily be expressed as a matrix operation, or in a matrix, which then can be used as in this sequence of matrix multiplications which are applied to our image. And once when we are there, then there is no further difference in what we do in this optimization process. So if I have this original image that I would like to recover from this image, so what I have to start with is this image. It is it is downsampled, blurred, and noisy. So applying restoration by energy minimization, where my energy function is expressed as stated here, I can restore this image that is my estimate of the original one. So I have it upsampled again, I have removed blur, and I have removed noise from it. Of course, nothing of that is done ideally, but it is still improvement compared to what we have to start with. And then we can go on and adding some more, let's say, so far we didn't really change anything in this initial formulation of our energy function, or the main idea. We were just adding more and more matrices in our matrix multiplication to model additional types of degradation. But we can also add some, let's say, go a bit more general and address further, like more difficult problems. We can, for example, allow spatial variability of the regularization parameter. So essentially, we can say that the amount of regularization that we want to impose is not necessarily the same for the whole image. We can, in some automatic way, have this tuned differently and say, oh, okay, in this region, I would like to have less of regularization, which will mean I will suppress my variations in intensities less and have more trust in my data, so keep the original values untouched, for example. By that, I can essentially, for example, preserve texture. And now this is an example what I can achieve. This is my noisy input. And this is how the output, the estimated original, would look if I use total variation as a regularization in my restoration by energy minimization. And then if I compare that with this new suggested version to have what is called an adaptive total variation, then I see that there are these regions which are not so flat, which I know that they shouldn't be. So the texture which is then quite desired in certain regions of this image is preserved, where as in the clearly homogeneous regions, I have then I have achieved this homogeneity, and that is simply because I removed quite much of noise in these regions where that should be done. There are other applications where very similar techniques can be used. So, for example, in painting can be used by using total variation as a regularizer in some energy minimization approach. That means that I can fill in some regions which I want to get rid of. So, for example, this text, if I want to remove it from this image, then I should also be able to fill in the missing details. And that is then done by setting suitable constraints of propagating the neighborhood that or neighboring function values in the missing parts, and that can also be done with suitable adjustments of the same model, which is then energy minimization by TV regularization. There are other applications. You can do segmentation, you can do a number of other tasks by using energy minimization, by using TV as regularization. So in that sense, this machinery, this algorithm is quite useful, and therefore it is good to have this higher level understanding and get these main ideas behind, since then it is very easily adaptable to a number of different scenarios that you may encounter. Okay, now just to add a comment that the content of this lecture will appear in your lab too, in the task noise modeling and image restoration, where you will get a chance to try to estimate noise in an image, that you will then try to use the mentioned measures for quality assessment. So you will use PSNR and SSIM, Structural Similarity Index, to compare different noisy and denoised or deblurred images, and then have some practice on what it means, how to use it, what do we like, what appeals to our visual system, and what is maybe not, what is somewhat contradicting the measures that we have from what compared to what we see. And then you will also see a bit of how image restoration can be done by regularized energy minimization in both cases of denoising and deblurring in presence of noise. So hopefully after this lab, you will have some good feeling about all the topics that we discussed. And of course, since this lab then also somehow covers the previous 2 lectures, which are related to image enhancement, you will have tasks related to filtering in spatial and frequency domain. You will also try a bit of working with 3D images, in this particular case, filtering such images. And then you will also have a chance to try template matching in the frequency domain, which we mentioned in the previous image, in the previous lecture, and which in my opinion is a very elegant algorithm to, and it's nice to try it. So that is what you will experience, what you will play with in lab 2. Let me then summarize what we have in these 3 parts of the lecture. We talked about image quality, which of course always is affected by the acquisition process and is always insufficient. So sometimes we can deal with what we get, but most from the acquisition, but in very many situations we would like to start our real image analysis with first slightly improving the images that we get directly from the acquisition, either by enhancement or by restoration. So, as we said, enhancement means that we are removing degradations, more relying on our subjective criteria. We want images to look better in some sense, or we want to perform restoration, which means that we would like our images to simply be that what they were supposed to be before they were degraded during the acquisition. We talked about noise, different types of noise that may be connected with different acquisition techniques. We talked about how to estimate noise. We talked about how to quantify noise, or how to quantify some quality of our images, mostly resembling to how much noise is present in them. And then we talked about restoration as inverse filtering, where we did most of the work in the frequency domain. And we particularly talked about Wiener filtering. We talked about the difficulties or challenges when we do inverse filtering, and that is dominantly high sensitivity to noise, and therefore this inverse filtering is usually used and can be effective when there is not, when the level of noise in the images is relatively small. Alternative is then to formulate restoration as inverse problem and to address it as via energy minimization, which then means that we are iteratively trying to find, to improve our guess of the original image that would, if put through the degradation process, the forward process, as we say, come as quite close or give identical result as the observed image that is the only one that we have and look at. So to find the image that is close enough, or very, as close as possible to the original degraded, to the original image before degradation, we are actually comparing the results of degradation, and we use that to decide what is the right, what is the suitable original recovered image. So we discussed energy minimization function. We discussed energy function, and we discussed different terms that appear in it. We talked about regularization, and in particular TV regularization, and we also commented on the possibility that to generalize the idea that is described in connection with denoising and then also deblurring to other types of problems. Somehow emphasizing applicability and usefulness of this energy minimization based approaches, which then can be very useful in a number of cases, number of situations. Some reading related to these topics is mentioned here. Again, Gonzalez and Woods have a whole chapter which is devoted to image restoration, and not even the whole chapter is addressed here, so you don't even need to look for the topics that are beyond these first nine sections. Then in the book by Schonka et al., there are a number of topics that are cover the content of the lecture, noise in images and how to measure their image quality, and also a number of topics on restoration. And finally, the computer vision algorithms and applications book. It does not have that much on this topic, but it has some parts. So it covers Wiener filtering, it talks about regularization in general, and I would say that this new second edition, which is available online, as I commented, has a bit more. So you might want to look at these two sections in the second edition and maybe have a slightly more of a content that is related to what we talked about today. This concludes the 5th lecture, and I am now announcing the following topic. So what will happen in the next scheduled session of the course, and is under this title of what I talked about today, will actually be not on, I will not repeat this lecture. We will do something else. We will organize a seminar session and I will talk more about it separately. But after that one, then the next topic that will be addressed in the course, and that will be again given by Robin, is on mathematical morphology, discrete geometry and topology. So some more theoretical mathematical concepts that will now be put in place before then we move on to segmentation and further along our image analysis pipeline.